Yeah, you can see the screen. Yes, okay. So I'm going to start. So good morning and welcome to a new lecture, yield line analysis of slabs. So this is the second session we have on slabs, and today we're going to look at the using optimization in the yield line analysis of slabs. Okay. Okay, just a reminder. This is what we did. We talked last week about the sign convention that we use for moments. We use the right-hand screw rule, and we went through this example here. Okay, and we use the left-hand side screw rule to obtain the rotation vectors. And I think we did two examples. We did a one-way slab, this one here, and then we did a two-way rectangular slab. Yes, is that right? Yeah. And we did a two-way rectangular slab that we completed last week, and therefore we what we're going to do today is use the same rules to analyze a rectangular slab. Okay. And this is the slab we are going to analyze. Okay. So what we have a slab which is 3 meters long, 3 meters in the y direction, and it's 4 meters in the y direction. So in the x direction is 4 meters, in the y direction is 3 meters. Basically, it's the same slabs that we did last week. It's exactly the same slab. Okay. Given the moment in the x direction is the moment of resistance in the x direction is m, and the moment in the y direction is 0.4 m. Okay. The difference between this example and last week's example is that in this case here, we assume a yield line pattern, a typical yield line pattern here, but we don't know where the yield line starts. So we say this length here is x, and we use symmetry, so we have x, and therefore this length here is 4 meters minus 2x. Yeah. So we are using the yield line pattern, but we don't know what the length x is, and we want to determine what is the optimum value for x. What's the optimum value for x for this slab? Okay. The slab is simply supported on all 4 sides. Now, as before, we have the slab here divided into the yield line divides the slab into 4 regions: region A, B, C, D. A and C are identical because we have symmetry, and the same for B and D. They are identical. Okay. We determine the moment vectors in red here. Okay. And we have the rotation vector in blue. Are you okay with the vectors? How to determine the vectors for the moment and the rotations? Okay. So once you've determined the vectors for the slab for each of the regions, which I've done here, the next step will be to determine the external work and the internal work for each region. Okay. So you start with the internal work, for example, and you determine the internal work for A, for C, for B, and D, and add them up. You add them up together to give you the total internal work. And then we do exactly the same for the external work for A, B, C, and D, and add them up together. So let's do it. Okay. So this is exactly what we did last week. All right. And this is the, if you want, the regions for each region, A, B, C, and D. We have the moment mx, that's the moment in the x direction, the moment of resistance in the y direction, the length of the yield line in the x direction, the length of the yield line in the y direction, the moment about the x-axis here, the rotation about the x-axis, and the rotation about the y-axis. All right, is that clear? So starting with region A, here, this is region A. This is the vector moment, the moment vector here in red. So when you project onto the x-axis, okay, you can see this gives you a positive moment in the x direction. This is negative projection. When you project it onto the x-axis, is negative. So you got m, and m projected on the x-axis, because on the x-axis we have m. Okay, so and it's negative, as I said, because it's opposite of the x direction. So we have minus m. When you project these vectors here, again, the rotation and the moment vectors on the y-axis, these two here, the components of these two vectors on the y-axis will cancel each other. And this one, the projection of this vector on the y-axis gives 0. So therefore, the net is 0 on the y-axis. Similarly now, if we take the yield line, this is the yield line here. That's the yield line from region A. This is the yield line. When you project this yield line onto the x-axis, you get 4 meters. That's this length here. And then when you project this yield line on the y-axis, it gives you 1.5 meters. Okay, 1.5 meters. Then for the rotations, okay, so we have, this is the vector rotation. The region A rotates about this axis here, this edge, this side, if you want. Okay, this is the axis of rotation is here. So therefore, the vector rotation, you can see, is about the x-axis is minus, because it's opposite the direction. So we have a minus here, so that's minus, and the rotation is equal, the rotation of this slab, of this region A, about this axis will be 1 over 1.5. Okay, will be 1, which is, because remember the maximum displacement is 1 out of the screen. So we have 1, and then this distance here is 1.5. This is 1.5. So therefore the rotation is 1 over 1.5 with the minus. Okay.
Hello, sir.
Yes.
That is the length S of A are supposed to be 4 plus 2s. Since the
What's the question? Sorry, can you repeat the question?
The question is the length of the length S of A. The projection, the total length of A is supposed to be 4 plus 2x.
The projection, this region A, this is the yield line, okay?
Okay.
So when you project this yield line, when you project it onto the x-axis, it gives you 4 meters. Okay? And when you project this yield line again on the y-axis, on this axis here, you can see that it's 1.5 meters.
Okay, the total length of the slab is 4 meters.
You don't take you take the projection of the length, you project it on the x-axis and then the y-axis. Okay?
Okay.
You don't calculate the length, you project it on the x-axis and then on the y-axis. Is that clear?
Okay.
Yeah, you project, because we have got x-axis and the y-axis. Okay, we are projecting the length, this length, we project it onto the x-axis, so it gives 4 meters.
Okay.
Okay, so now for region A, we multiply mx by lx by theta x plus my ly times theta y, which gives me 4m over 1.x, because here you got minus by minus is a plus, so you get a plus sign, okay? And when you add them up together, you get 4m over 1.5. You can see that A and C are identical. You don't need to do all that for C because you have symmetry. So you can say that for C the work is also
Sir, this work
over 1.5.
This work, is it external work or internal work?
That's the internal. This is the internal work. Okay.
Internal work.
Yeah, internal is moment times the length of the yield line times the rotation. So you multiply moment by rotation, and then you multiply by the length here. That's the internal work. Okay. So you do it for region A, and C will be identical, and then we do the same for region B and D. I mean, B and D are identical, so you do it only for B, and D will be the same, okay? So if we look at B, we have, these are the vectors. So when you project these vectors here, these two vectors, when you project on the x-axis, you get M. So we have M here, okay? When you project these two vectors on the x-axis, sorry, I repeat. When you project these two vectors on the x-axis, they cancel each other, so you get 0, okay? And when you project them on the y-axis, you can see that you get a positive component, okay? And it's 0.4 M, okay? Now, the yield line, this is the yield line for region B. This is the yield line. So this is the yield line for region B. When you project it on the x-axis, you get X, which we have here. And when you project this yield line on the y-axis, here, you get 3 meters, which is what we have here. So that's the length on the projected on the x-axis and the y-axis. X is unknown. We are looking for X. Okay, that's the optimization. So we don't know what X is, so we just call it X here. For the rotations, this is the vector. This is the vector rotation. Okay, that we have. So when you project it on the x-axis, you get 0. Okay, because it has no component on the x-axis. And on the y-axis, the rotation, remember the displacement here is 1, out of plane. You got 1. So the rotation for this region is 1, out of plane 1 over x. 1 over x. Okay, 1 over this length, which is x. And then when you multiply mx, lx, theta x plus my, ly, theta y, it gives you 1.2 m over x. And then you just copy this into D. You don't have to do all that for D, okay? Because they are identical. We have symmetry. So we have for D, we also have 1.2 m over x. And these are the works. These are the works for region A, B, C, and D. And the total work will, the total internal work will be the sum of all this. Okay? Is that clear? Yeah?
Hello, sir.
Okay. Is that clear? Yeah?
Hello, sir.
Are you asking the question?
Yeah, internal was supposed to be moment times theta, not moment times length times theta.
Yeah. This is theta. The rotation is the rotation of the region.
I think internal work supposed to just be moment times theta.
Yes, but remember, what are the units? The moment is over the entire length. I explained this last week.
Okay.
Moment is over the entire length of the yield line. Okay, because the units of the moment in this for the yield line, the units of the moment are kilonewton meter per meter. So you need to multiply it by the length because it's per unit length. Okay? The units of the moments are kilonewton meter per meter because it's applied over the entire length as we saw last week. Okay, you can see here. You can see the moment is applied over the length. Yeah, so you need to multiply it by the length of the yield line to give you the moment. Okay, so moment times length of the yield line times rotation. So it's always mx, lx, theta x, my, ly, theta y. And the total here you can see the total internal work is twice 4m over 1.5 plus twice 1.2 m over x. And then if you simplify here, you get 2 times m times 2.67 plus 1.2 over x. Okay, this is by adding these together here, and you can take 2m outside the bracket, which gives you 2.667. Okay, which is effectively 4 over 1.5. Okay, and then you have 1.2 over x. Is that clear? Okay, the 2.67 here is 4 over 1.5. Okay, 4 over 1.5 gives you 2.67. And this is the external. This is the internal work. Now we are going to work out the external work for this slab.
Hello, sir.
Yeah.
How did you come about 2 times 4m all over 1 over 5?
It's the internal for each region. So you add these two together, 4m over 1.5 plus 4m over 1.5. So that's twice.
Okay.
Okay, and the same here, you've got 1.m over x and 1.2 over x, so it's twice. Okay?
Okay.
Now, looking at the external work now, so we have 4 regions. So we do the external work for A, and we multiply it by 2. And do we do the external work for D or B, and we multiply it by 2 in the same way. Okay, so let's do that. So this is region C. A will be the same. So this is the region. Okay, we have the length is 4 meters. So we have x and 4 minus 2x. The length here in this direction, in the y direction, is 1.5. So what I've done here, I've divided this trapezoidal shape into 2 triangles and a rectangle to make it easy. Okay. So what is the? So how do we calculate the external work? The load W, you have UDL on the slab. Yeah, W times. What do you times it by what?
1.5 into.
Remember the units of the UDL. The unit of the UDL is kilonewton per meter square. So I need to multiply the UDL by the area, and then multiply by the average displacement. Okay, because the work of UDL is the UDL times the average displacement. Okay, so we do that for each of these 3 regions here. Okay, so for let me explain. For this slab, for this triangle, or let's start with the rectangle here in the middle. Okay, so we have W times the area. What is the area of this triangle, of the rectangle? 4.2. 4 minus 2x times 1.5. So here this term is the area times the average displacement. Remember the displacement there is 1. The displacement here at the maximum curvature is 1. So we take the average displacement. So it's half of 1. So 1 over 2. Is that clear? Okay. Yeah. Plus, now for this triangle, we have the UDLW times the area. What is the area of the triangle? X times 1.5 over 2. So here, this inside the bracket is the area. And then we take the displacement, because this triangle, the centroid is 1/3. So you have 1/3 for the displacement, okay? Because we have 1 here, so there you have 1/3. Okay? And you multiply by 2, the 2 here, because we have 2 identical triangles. Is that clear? So your total external work for C is this one here. And then you simplify, you expand the brackets and you simplify it, and you should, and then remember the external work for A and C are the same. So in other words, this here you multiply it by 2. Now we do the same for region D or B. So this is the region D. We have a triangular shape.
What, sir? What is the deflection? Deflection is half.
When you have a UDL, like here, you have a triangle, rectangle, and you have a UDN, the displacement there is 1. Okay? The displacement is 1. So what is the displacement at the centroid here? Half. If the displacement is 1, the displacement in the centroid, in the center of the rectangle, is 1, which is what we said before, the average. Okay? So if the displacement is 1, the displacement there is half of that. Is that clear?
Yeah.
Okay? And the same for the triangle. If the displacement here is 1, the displacement there is 1/3, a third, because the centroid of the triangle is at 1/3. All right? Now we do the same for region B and D. So this is region B, D here. So we have 3 meters, and we have X in this direction. So what is the external work for this triangle? W times, what is the area? 3 times X/2, and then times what? 1/3. Okay, so that's it, simple. Okay, W times the area times 1/3. Because D and B are identical, so we have the external work for D is the same as for region D. And now I'm going to add them up together. So we have twice the external work of so basically you have WD plus WB plus WC plus WA. So we have twice that plus twice the external work of B. So I've multiplied here by 2, and then you expand the brackets, which I have done here. I expand the brackets, okay? And then when you expand the brackets and you simplify, you get 6 times W minus W times X. You can take the W outside the bracket times 6 minus X. So the total external work is W times 6 minus X. Okay, so the total is 6 minus X. Is that okay? Right? So now what do? So we equate for equilibrium. Yes?
Why didn't we express the deflection? The deflection as a function of theta, as a function of the angle, as we did in beam analysis.
I don't understand. What's your question?
My question is, why didn't we express deflection?
In the early design we use theta. As we find out the angle theta, and we just express in terms of theta.
Because for the internal work, it's m theta. It's moment times rotation. This is what we did in the plastic theory before. The work of a moment is moment times rotation.
Yes,
force times displacement.
For internal work, for external work, why is theta not there? Why is it not the length times theta?
Because we are talking here about the external work. The external work is the work of W. Okay? What is your external load here? Which load do you have? External load. What is the external load here?
It's an area load.
Well, the external load is W. It's the UDN applied on the slab. And the work of UDN, the work of the load, is the load times the displacement. Okay?
You assume that the displacement is 1.
What's the question? Sorry?
I said you assume that the displacement is 1.
We assume displacement as 1. That's what it is.
Oh yeah. We assume the displacement is 1. Yes. Okay.
Okay.
All right. So we have got the external work. We've got the internal work. So now we're going to. That was the equation for the internal work. Okay. So I'm going to equate these two here. For equilibrium, we have the external work equals to the internal work. All right. So we have got these two here equal. So we have W6 minus X equals to this. And then what you can do, you can manipulate this here. So you got 2.67X plus 1.2 over X. Okay. And then I'm going to take the 6 minus X down here to give me W. So W is 2M, okay, times this term divided by 6 minus X. Is that clear? So it gives me that. And then I can either, or if you want to express M, you have M is W times this divided by this, whichever you want, whichever way you want to do it. Either you express M as a function of W, or you express W as a function of M. It doesn't matter. Okay. Now, how do we obtain? So if we take the expression of the moment, this is the expression of the moment. The moment is equal to the UDN times this expression here, which is a function of the distance x. From a purely mathematical point of view, okay, if you want the optimum value for m, what do? You differentiate about x equal to 0. You agree? Yeah? So because I've got m, I've got the moment is a function of x. So if I want the optimum value, then I need to differentiate this expression of m here about x equal to 0. Okay? Right? So we need to w cannot be 0, obviously. W cannot be 0. So we only need to differentiate this ratio here about x and put it equal to 0, which is what I've got here. If you do that, can you take pen and paper? I just want to make sure that you know to do it, because you might get an equation like this in the exam. Can you differentiate this, please, on your own, and see whether you get this expression or not, please? Can you do that? I want to give you like 3 minutes or 4 minutes. Can you differentiate this, please, about x, put it equal to 0, and let me know whether you get the same expression here. Okay, I'm going to give you 5 minutes. Because I want to be satisfied that you know how to do it. You might get a question like this. The exam is on the 9th, isn't it? The exam is on the 9th. You see the timetable? No. 9th. Yes, it's out. The timetable is out. You need to check your portal. Yeah. Your exam is on the 9th of November, of December. Check the timetable, yes.
It's TCA.
So,
Is it TCA?
TCA, yeah. So we have the whole day from 9 to 10 p.m. From 6 o'clock to 10 p.m.
Àwọn VD quotient. Quotient 2 plus 2.4. So that makes 3, 4, 0.
Do you know what I said? You should know the equation, isn't it? If you have u over v, if you call this u and this v, isn't it? You know the equation. Yeah. So it would be the derivative of this one or times this one minus the derivative of this one times this one divided by this squared. Okay? And remember the denominator cannot be 0, so it's only the numerator. Okay? So when you differentiate, the denominator cannot be 0, so you are looking only at the denominator, at the numerator at the top, equal to 0. And when you simplify, you should get this expression. So I just want to make sure that you know how to do it. Did you get that? Okay, carry on. Excuse me. Online, are you working on it?
Yes, sir.
Okay,
Yeah.
carry on.
This is over 80. That's correct. And this is going to so your sign conversion and this one for okay, so we subtract.
Wait, you get a second to time this. See, when you have expressions like this, 6x minus x squared by 2.65, this is equation 1. And you should apply product rule. Divided inside. A by b, this is equal to any function, first function into derivative of second function minus second function into derivative of first function. And what you need to do, this is the first function. I'm just giving 6x minus x squared into just put it how it is. Divided of this just need to multiply that. And just explain it to the answer.
Are we okay? Have you got it?
Yes.
Have you got it?
Yeah.
Online. Okay. Right. So anyway, so when you have differentiated, as I said, you take the top, differentiate the top times the bottom, minus the bottom here times the top over this squared, and bearing in mind that the denominator cannot be 0, so you basically are looking only at the numerator. So when you take the numerator and you simplify, you should get 5.33x squared plus 4.x minus 14.4. Okay? after simplification. Now, this is a quadratic equation. Okay, it's a second order equation. And I'm sure you all know how to solve a second order equation. It has the form ax squared plus bx plus c equals 0. So a is 5.33, b is 4.8, and c is minus 14.4. So you can use the delta equals b squared minus 4ac, and then the solution will be minus b plus or minus square root of delta over 2a. Is that clear? So if you do that, you will find one solution. The other one will not be acceptable. You find one solution which is 1.23. So you find x is 1.23 meters. All right. What you do then? You take this value of x, 1.23, and you substitute it here into this equation of m, and that will give you the optimum moment. Is that clear? Okay, so differentiation will give you the value of x, 1.23 meters, and you substitute it into the equation of m to give you the optimum moment. Is that clear? Yeah? Okay. Now always check that your values make sense. I mean, because if you make a mistake and you get an x value, I don't know, 5 meters or whatever, which is more than the actual length, obviously you need to reject it, okay? So here you've got, although you have got 2 possible solutions, but there is only one acceptable, okay? Which is 1.23 meters. So I'm going to substitute this, equate this x value back into m to give me, this will give me 0.66 W. So m, so the optimum moment is 0.66 W, or if you want, W is 1 over 0.666, which is 1.53 M. So either you know M and you determine W, or you know W and you determine M. Okay, I did explain last week that normally in practice, you will get the moment of resistance for the slab from the code. So you can use, for example, Eurocode 2, which is for reinforced concrete. So if you use the Eurocode 2, you can get the moment, the expression of the moment from the Eurocode, because you know the size of the slab, you know the edges, you know the reinforcement, everything. So the code will give you M, and then if you use this equation here, this one here, you can predict at what load the slab will fail. You can predict at what load the slab will fail, okay? The other alternative will be to test the slab in the lab. So you take your slab with the size, you rest it on 4 edges, on 4 supports, and you load it with the UDL until it fails. So when you load, so when your slab fails, what do you know? You know the failure load. So when you know the failure load, when you know the collapse load, you use this equation, it gives you M. Okay? So it all depends on the nature of the problem that you have from a practical point of view. Either you use a code to give you M and then you can predict the collapse load, or if you want to test, if you do a testing lab work, if you do lab work, you can get the collapse load from your lab experiment, and therefore you can get M. And then you can compare. If you would, then you compare the moment from the code with the moment that you get from the experimental results. You can do that. Is that clear? Are there any questions? Okay. So this is a very good example where we see what's the how to use optimization in this case. Okay. If you have no more questions, I think we're going to move to the next. Oh yes, I can use a graphical solution. Okay, that's the algebraic. The algebraic solution is you differentiate. If you do that, okay. If I take this is the expression of M equals W. Okay, if I do M over W, M over W is 6x minus x squared over this. Yeah. I can plot the graph of M over W versus X. I've done it here. So you can plot this graph here. Are you good in maths? You can plot, no problem. So if you plot M over W versus X, this is what you get. You get this graph here in green. And you can see that the optimum value is just short of 0.7. We got 0.66, isn't it? So if you do it correctly, can you see there? Yeah, it's about midway. 0.65, 0.66. Can you see that? So if you do it graphically, you can get a good estimation. If you, I haven't done it on graph paper, but if you do it on graph paper, you get a very good approximation for the solution of M over W. It gives you the optimum value. So two ways you can do it graphically, like here graphically, or you can do it mathematically from algebraic by differentiating and obtaining the optimum value from that.
Sir,
Yes.
if it comes out in the exam, can we plus a graph?
Yeah. You can do whatever you want. You have the whole day. You have 4 hours, so you have a lot of time. 4 hours. We allow 4 hours because the exam is normally 2 hours, but we give 4 hours because of that. So maybe you can you have to do it if you want to do it graph paper and then scan it or whatever, and then you can upload it with your exam. Okay. So you have time to do you have the time to scan or to take photos and upload with your exam. Okay, that's okay. There is allowance for it. Okay, but you have completely unless I specifically say use the algebraic solution, and usually I don't, then you are free to use any solution that works for you. Okay, I don't mind. I like the graphical representations because you can see exactly what's happening. You can, because the graphical representation shows you that it's not linear, that it progresses like this, okay, and then reach a peak and then gradually drops down until it gets to the value of 0 here.
Hello, sir.
Yeah.
How are we going to get, if we want to use graphical method?
If you are going to get what, sorry?
If we want to use graphical method, how are we going to get the parameters to plot the graph, the value of S?
To get the equation, that's the equation.
Yeah.
The value of S, are we going to guess the value of S?
But if X is 1, if X is 2.
No, we can assume the value for X. Y.
You assume your values for X. So you can have 1, 2, 3, 4, 5, whatever. Yeah. You know that the top here, you know that this one, can you see that? This is going to be equal to 0 when X is equal to 6. So straight away you can see when X is 6, you get 0 there. Okay? So then you can choose your scale. You can choose your scale in the x-axis. So you have 1, 2, 3, 4, 5, 6. Okay? And therefore, what you do, you substitute values of X, you get M over W. You do it like a table. The best way is to do like a table where you have, where you have values of X. So you do like a table. You do a small table here for the values of X. You choose your values of X and you get M over W. Okay? Is that clear?
Yeah.
Yeah.
Okay. Now, can we move on to the next example? Have you got any questions? Is that clear? Okay. Now the next example is a triangular slab. Okay. We have a triangular slab supported on 2 sides. This example is a little bit more tricky. The reason being, it's a triangular, but it's not like a regular triangle. It's a little bit it's an irregular triangle, so obviously the geometry is a little bit tricky. But I've decided to do this example because it's a good example to show you how to use optimization to solve a complex problem. Remember, you're doing an MSc, so you need to be challenged a little bit. Okay. So what we have a triangular slab. Okay. So this is the problem we have. We have a triangular slab A, B, C. The slab is simply supported on A, B, and AC. In the X direction, the moment is given 0.565 M, and the moment of resistance in the Y direction is also given is M. So in the Y direction you have M, and in the X direction you have 3/4, 0.75 M. So these are given. Okay. So this is the data we have been given. That's the slab, and the slab obviously is subjected to a UDL applied over the entire length. The other data we are given is that the angle here between AB and AC is 70 degrees. That's all we are given. Okay? That is all we are given. Sorry, and also given AC, you need the length. So AC is 8 meters, and AB here is 6 meters. So this is 6 meters, this is 8 meters, and the angle is 70. Clear? Yeah. What we want to do here, we want to find the optimum yield line for this slab. First of all, how do you think this slab, when you load it, how do you think it's going to fail? Just imagine in your head that you've got a slab supported on these two edges and you load it. How do you think it's going to fail?
Along the edges, along the...
A yield line, one single yield line here, somewhere there.
Yeah, kind of.
Yeah. So you can have one line here, isn't it?
Yeah.
Definitely. Because if it's supported on two edges like this and you load it, there will be a crack forming somewhere that will split it into two, and then it will fail. Clear?
Yeah.
Okay. So really, this is what we have. Okay. What I have here, this is the yield line. Please follow this carefully. Okay. This is the yield line that I've assumed, AD. So there will be one single yield line, AD. We don't know where this yield line is going to form, so I'm going to assume it's forming at an angle theta from AC. Is that clear?
Okay.
Yeah, so we assume theta. And what we're going to do now, we are going to find what is the optimum angle theta. What is the optimum angle theta for this slab? Okay, now I did some geometry here because when I work out the rotations, I will need the perpendicular distance here. So I've worked out, I've extended this line here, and I've extended this line there, which passes through this point, okay? And then I've got the perpendicular distance here, DE, I call this point E and this point D, and I have the perpendicular distance here, DH. Is that clear? So this is my slab, A, B, C. This is my yield line at an angle theta, and I've called the point here D, so to give me the perpendicular distance, HD and DE. Okay? What I've got here, do you agree with the vectors? Sorry. Do you agree with the vectors moment? Do you agree with the direction of the moment vectors here? Use the right hand and check it for yourself. If you start with this side, you've got this, isn't it? You've got more, you've got this, and this is the thumb direction. Okay? The moment is coming for this region here. The moment along the yield line is coming out of the screen towards you, and the thumb will give you the direction of the vector. You agree? Okay? And then the other vector obviously will be equal and opposite direction. Sorry, yes?
Please, can you repeat that, sir?
Theta is unknown. Okay, we are going to optimize. We need to find what this, all we know there is a yield line, one line. This is the crack line, if you want. This is the yield line. And the angle theta is unknown. We need to find theta. Okay? So theta is just an angle that we need to find. Okay, now the rotation vectors. Do you agree with the direction of this vector here for the rotation? Using the left hand, the rotation is going from you into the screen. Okay, it's going from you into the screen. So therefore, that's the direction of the point. Okay, so it's going like this. This is the rotation. The slab rotates like this. Okay, and this is the left hand, and this is the direction of the vector, the vector rotation there. Okay. So we've got everything here now that we need to start the internal and the external work. Okay.
Sorry,
So
question.
So the yield line splits.
Sorry, I have a question.
Yeah.
Yeah, I wanted to confirm now that the perpendicular distance origin point from E is at the midpoint of A and C. Is that right?
Sorry.
The perpendicular distance originating from E is at the midpoint of A and C. Is that right?
What's the question?
The perpendicular distance from
Originating from E. Is it between
at the center of B and C?
A and B, A and C? Is E at the center of A and C?
No.
At the center? No, they're not at the center. No, you mean if E is in the middle?
Yes.
No, it's not. Not necessarily. Okay? I mean, the drawing here is a bit misleading, but E is not in the middle, okay? We don't know. This is an angle theta, okay? And the perpendicular gives me this point A, okay? And this point H. But they're not in the middle, no. Not necessarily, okay? This will be in the middle only if this triangle is isosceles. Do you understand? If the angle here, if this triangle was isosceles, then yes, this will be in the middle. But we didn't say that. We don't know. Okay, so it's not in the middle. Okay, all we know it's 90 degrees. It's a perpendicular. Okay, that's all we know. All right. Okay, shall we start now the external and internal work? So this is the slab with all the angles. I've got this is 70 degrees. I've got the angle theta here. Do you agree that this angle is theta plus 20? If this is theta, if this is 70, if this is theta, what is the angle here? Come on, work it out. Piece of paper. What's the angle there? What's this angle here?
90.
What is this angle?
90.
90. Okay. What is this angle here? This one? 70 minus theta. Okay, this is 90.
Okay.
This is 70 minus theta. Yeah, and then the sum should be 180. So do that and tell me whether you get theta plus 20. Clear?
Yes.
Yeah. I repeat, this is 90 degrees here. This angle is 70 minus theta gives me this angle here. And therefore this angle, because the sum is 180, this gives me theta plus 20. Clear? Okay, clear. Now, I'm going to call the vector here to distinguish. This region is A. I call this region A. A, B, D, I call it region A. And A, D, C, I call it region B. So this angle, the rotation vector here is theta A, and the rotation vector here is theta B. Okay? So, let's see. Let's go slowly, okay? Let's go slowly. Now, the internal work is moment times length times rotation. Okay? Now, for each region, for region A and B, we need to take the moment in the x direction times length in the x direction sin theta x, etc. Okay? And add them up together. So the total internal work will be the internal work of region A, okay, this one, plus the internal work of region B, this one. Okay, this is region B. Clear? Now, let's follow, stop writing and let's just listen to me because I want to explain it. Look here, concentrate on region A first. Concentrate on region A. So, mx, this is the vector. Can you see that? So this vector, when you project it onto the x-axis, okay, do you agree that on the x-axis we have 0.75 m? Do you agree that the component of this vector on the x-axis is negative?
Yes.
So we have minus 0.7 m. This is mx. Done. Now, what is the length? Can you see this yield line here, AD? What is the projection of this yield line onto the x-axis? Do you agree it's AE?
Yeah.
You agree? Okay, so that's LX. Okay, now, rotation. What is, can you see this vector here? We are looking at region A. Can you see this vector theta A? Yeah. This theta A, the component of this, the projection of this vector onto the x-axis, do you agree it's, first of all, it's negative?
Yeah.
And do you agree it's theta A cos 70? Look here, if I draw a horizontal line here, look with me, follow the mouse. If I draw a horizontal line here, do you agree that the angle there will be theta, will be 70?
So, is it alternate angle?
Sorry? Yes, alternate angle. Okay, so if I draw a horizontal line here, horizontal, the angle there will be it will be 70. So therefore, the projection of this vector onto the x-axis will be theta A cos 70. Clear, everyone? Yes? Okay. You do the same now for this region B. Okay. For region B, we have, this is the vector. This is the vector here, moment vector. So when you project it onto the x-axis, you agree with me, you have m. Sorry, on the y-axis. You have m, isn't it? I'm doing the x-axis first. Do you agree with me that this vector onto the x... now let's finish region A, sorry. Let's finish region A. So now I'm going to project onto the y-axis. So this vector here on the y-axis is m. Yeah, and it's negative because it's going down. So we have minus m. Now, this yield line projected onto the y-axis, do you agree it's dE?
Yes.
So we have dE. Now, this vector here projected onto the y-axis now, do you agree it's theta A sine 70? And it's negative because it's going down. That's it. So now, the first bracket from there to there, this is only for region A.
Hello, sir.
Yes.
What are you using to multiply cos 70? Is it theta A?
Yeah. This is the projection of this vector on the x-axis. So you have theta A cos 70 because this angle, you have 70 here. So alternate angles. So you've got 70. If you draw a horizontal line here, you've got 70. So therefore, you have theta A cos 70 is the projection on the x-axis. Okay?
Theta A times cos 70. How did you get that, sir?
It's the angle is 70 here.
Okay.
Sorry, just 1 minute. trying to I'm trying to draw a line. I don't know how to do it here.
Just,
Oh, come on. Look here, if we draw a line here, if we draw a horizontal line, this angle is 70. Okay? Between the vector and the horizontal line, it's 70. So therefore, the horizontal component of this vector will be theta b cos 70. Okay? It will be theta a cos 70. That's the horizontal component of the okay, so if you draw a horizontal line here, okay, the angle there is 70, so the horizontal component will be theta a cos 70. Okay? Which is what I've done here, okay? So it's theta a cos 70. Now when you take region B, which this region here, this angle, this vector here has no component in the y direction. You agree?
Yes.
It only has a component in the vertical, in the horizontal direction. So there is nothing here for the vertical. There is only the horizontal, okay? So we have, so if you take this moment vector, this one here, and you project it onto the x-axis, we have m, on the x-axis we have 0.7 m, okay, times, what is the length of this yield line on the x-axis? A, E, yeah. And what is the moment, what is the projection of this vector on the x-axis? Theta b itself.
Yeah.
Okay, and then there is nothing on the y-axis because this vector has no component on the y-axis. And therefore here we have, this is the total internal work for this slab. Okay, so the first part, this is region A, and the second part here, this one is region B. And the total is your total internal work. Okay. Further, what I've done here, I have substituted. Can you see this rotation here? This rotation, the rotation theta A, is equal to 1. You know the maximum displacement is 1 along the edge. We have 1. Yeah. We assume we have a unit displacement. So this vector, the rotation theta A, will be equal to 1 out of plane. We have 1 over the perpendicular distance hd. So I've substituted theta A here by 1 over hd. Minus and minus becomes a plus, so that's gone. Okay, and theta A is 1 over hd. Similarly, for theta A here, I've substituted by 1 over hd. And finally, theta b, can you see theta b? The rotation theta b will be equal to 1, which is here, 1 out of plane is 1, over dE. 1 over dE. So it gives me this. Okay? So I've substituted here theta a and theta b by the length. Right? And then, but look at the triangle here. Do you agree that cos theta is AE over the hypotenuse AD?
Yeah.
You agree?
Yes.
And do you agree sine theta is the opposite DE over hypotenuse AD? Okay, so I've got that. So what I'm going to do, can you see here? I've got AE and I've got DE. I'm going to substitute this AD and DE, okay, AE and DE here by, respectively, cos theta AD and sine theta AD, which I have done here. So I've substituted this here, AE. AE is cos theta AD, and,
Sir,
yes,
screen.
Screen.
Okay, so I've substituted AE and DE here by these expressions. So I've got now this expression here. Okay, so the only thing left is this AD here. Now I have rearranged it. I've got AD here over HD, and I've got AD over HD here, and I've got AD over DE there. Okay, now we know, can you see this angle here? Theta plus 20. What is cos of this angle? The adjacent DE, HD, sorry, over the hypotenuse AD. You agree?
Yes.
Yeah? So we have cos theta plus 20 is equal to the adjacent, which is the HD, over the hypotenuse, which is 80. Okay? And I'm going to substitute here by, can you see here we've got AD over HD? So AD over HD will be 1 over this, 1 over cos, okay? Which I have done here. So now I've got 0.75 when I substitute times this expression in bracket plus m times this expression in the bracket plus 0.7 m times this expression in the bracket. Okay? You need to know your trigonometry. Okay? You need to know your trigonometry. The good thing is that if you get an example like this, in the exam, you've got access to the internet, so you can look at the equations for the for trigonometry. Basically, let's leave it as it is for now. Let's do the internal work first. Let's do the internal work. The internal work, the external work is the external work for region A plus the external work for region B. Or I can do the lot. What is the external for this slab? Well, it will be W times the area times this length. Or if you want to do it in 2 regions, that's fine, okay? So I've done it here. For region A, it's W times the area A, this area, times a third, 1 over 3, okay? Plus, for external, for the region B, we have W times the area times, times a third. If I take W over 3 from both and take it outside the bracket, so it's W over 3 times area A. What is area A plus area B? Is the area of the whole slab, which is, can you see the area of the whole slab? It's AB, okay? It's AC, sorry, times the height. Times the height, isn't it? You know the area of a slab? Is the height times the base. Yeah? So the base is AC. What is this height here? Do you agree it's AB sine 70? This height. Do you agree the height here from B down, this height, this perpendicular distance? Do you agree it's AB sine 70?
Yeah.
Yeah?
Yeah.
So it's AB sine 70. We know AB is 6 meters. We know AC is 8 meters. Substitute AC and AB by 8 is 6. Sine 70 over 2. And everything is known. So it gives me the area of the slab is 22.56. Because we know all the dimensions of the slab. Okay? So when you do that, and you substitute back here, so you have W over 3 times the area of the slab, 22.56, it gives you 751 W. So the external work in this for this slab is 7.51 W. And I'm going now to equate the internal work with the external work, okay, and solve for the optimum value. Is it okay or not? Yeah? Okay, so what you do then, so what you do then, you equate the external work, okay, that's the external work, that's the internal work, sorry, here, equals to the external work, and then I have rearranged, all I'm doing here is rearranging, so I've taken M outside the bracket, so it gives me 0.75 times this, plus this one here, plus this equals 751. What I've done, I've put f theta. Can you see this expression, this long expression here? I've called it f theta, okay, times m. Now, so we have m times f theta, this function here, equals 751w. Okay, or m over w is 751 over f theta. And f theta is this. Now, there are two ways you can solve this problem, okay? One way is graphically. So you plot a graph. What I've done here, I've taken the values of theta arbitrary, completely arbitrary values of theta from 0 to 45. If the triangle was at 90 degrees with two sides equal, the yield line will be at 45 degrees, isn't it? Yeah, it would be at 45, but because it's an irregular shape, it's going to be less than 45 anyway. Do you agree? Yeah, so theta is going to be less than, so I've taken what I've done here, I've taken values of theta in 5 degrees steps. So 5, 10, 20, then I've jumped to 20, then jumped to 30, 35, 45. So when I got closer to there, then what I've done, for each value of theta, I substitute theta into the equation of theta, in f theta here, which gives me m over w. So I got these values here, okay? Can you see what's happening here? For theta equals 30 degrees, I get f theta here 2.377. For theta equals 35, it gives me exactly the same value, 233. What does it mean? That means there is an optimum between these two. Yeah, so if you plot your graph, you have two values that are equal, so therefore your optimum is between these 2 points here. Okay, anyway, I've substituted the values here of f theta back into the equation, which gives me these values, all right? And you can see we've got m over w is 316. So therefore, definitely, there is an optimum value between 30 and 35 degrees. Using your calculator, you start fine-tuning. For example, you try 31 degrees, you start 32, 30, until you see that you've got your optimum value graphically. And what I've done here, I have actually, with further refinement, using a calculator, you will find that the actual optimum is actually exactly midway between 30 and 35, which is 32.5 degrees. Okay, it's exactly in the middle, okay, between these two values. And therefore, when you substitute here theta by 32.5 degrees, you get m over w 3.18. So the optimum value of m over w is 3.18. And this is using a graphical solution with the table and the help of a graph. Is that clear? So this is graphically it's semi-graphical. It's a little bit of a graphical representation, but also some calculations here. But I haven't used optimization, because if I use optimization, what should I do if I use optimization? What should I do? Exactly, because normally, if I want a precise answer, if I want an algebraic precise answer, what I need really to differentiate f theta above theta and put it equal to 0. And that will give me a correct solution of theta. I don't know if I've done it, let me remember. I might have done it. Okay. All right, I don't think I've done it. I think I've done it with somewhere. I haven't got the solution here, but you can actually what you could do if you are really good with trigonometry. I'm not asking you to do it, but if you are really good with trigonometry, you can actually simplify these expressions here. You can further simplify, and then you differentiate about theta. And you need to know, for example, when you differentiate sine theta, you get cos. When you differentiate cos theta, it's minus sine. Yeah, you need to know when you differentiate tangent, you get I can't remember, I think it's 1 over something. But anyway, if you know your trigonometry, it's not very difficult to differentiate this about theta, put it equal to 0, and what you would find that the algebraic solution will be very, very close to this as well. All right? Each problem is different. In this particular case, it's easier to do it graphically because you've got a complex trigonometric equation, so it makes sense in this particular case to do it graphically. Okay, but it can be done. It can be done. Algebraically, but it could be a little bit longer to do. That's all. Okay, so in this case, that's perfectly okay to go for an algebraic. To go for a solution like this. Okay, we're using a graphical representation. Any questions? Anything at all? Okay. As an extra tutorial, try it.
Sorry, I have a question.
Yeah, sorry?
Yeah. Based on the graph, does that mean that the optimal value is at the value of the graph?
Yes. So if you plot the graph of f theta versus theta, okay, if you plot theta versus theta, right, then what I'm saying is that you would find that between 30 and 35, you find that the two values here at 30 and 35 are equal. Can you see it starts you see it starts with 8.95, isn't it? And then it starts dropping, reducing, until you get to 32.37, and you get 237 again at 35, and then it increases again. Can you see it increases again? So it drops like this, and then it starts to increase again here. So therefore, between these 2 points, definitely is the optimum solution, because you have got a drop, then an increase again. Okay? You can try it. Okay? You don't have to do it, but you can try it. The other thing, as I said, if you want to do an extra tutorial, it's up to you. I might have the solution somewhere. Okay? If I find it, I will upload it. But you can try and optimize this by differentiating. Okay? Now, I would like to give you an extra tutorial question for you to try. All right? Sorry? Yeah. If you want to try the same problem, but this time instead of 0.75 here, m and m, you take m and m, simply. The reason I've given you this is that because what's going to happen, what's going to happen, let me show you. If you simplify this, if this is m and this is m, so you have the same moment resistance in both directions, you will find that this expression, you would find that this expression here will simplify enormously, because you haven't got 0.75 anymore, because you've got m and n in both directions, and you'll find that because of that, it does simplify, and therefore manipulating the the trigonometric equations here will become simpler, and therefore you can use an optimum solution. Okay, I think I will find a solution and upload it for you. But try it on your own, please. Try this one on your own. It's a very good exercise to practice what we've done today. Yeah, so it's a good way to go over the example again. Is that okay? Yeah. Any questions at all? No? Okay, I think we've done well. We didn't take a break, so it's okay to finish a little bit early. So I'm going to stop the recording. Any questions online? You okay? Okay, thank you. So I stop the recording.